Alright guys, today we're going to be talking about the ideal gas law. Now, as you've been going through the chapter, you've seen a lot of different laws and the observations that come with them. First we have Boyd's law. Boyd's law says that pressure is inversely proportional to volume. So if we were to graph this out, we would get a really weird relationship. All these laws are directly proportional, but not Boyd's law. When you graph Boyd's law, you get something funky like this. So we're going to see as pressure increases, the volume decreases. Likewise, as volume increases, pressure is going to go down. Okay? So that's what it means to be inversely proportional. One goes up, the other goes down, and vice versa. These other laws, Amonton's law says pressure is proportional to temperature. Charles' law says volume is proportional to temperature as well. And Avogadro's law says volume is proportional to the number of moles. For these, you get a straight line when you were to graph it. So if we were to graph Amonton's law, we would get pressure and temperature and a line like so. And as the pressure increased, the temperature would also increase. So if the pressure goes up, the temperature is going to rise. Also, if the pressure goes down, the temperature is going to fall. This relationship stays the same for volume, as we see in Charles's law. And lastly, the same thing occurs when you apply moles in relation to volume. Right? One property goes up or increases in value, the other property is going to increase by an equal amount. Okay? All these observations, all these different laws combine into what we call the ideal gas law. So it relates these variables that we've been studying and puts them all into one pretty easy to use formula. Now, PV equals nRT is the ideal gas law. You'll probably recognize pressure, volume, moles, and temperature, but what's this R doing here? This R is going to be the ideal gas constant, and it's going to ensure we get the right answer as well as cancel out all of the units we need it to. So R is equal to 0.08206, and the units for R are a bit daunting. So the units are liters times atmospheres divided by moles times Kelvin. All right, so that's what goes on the end of here as a unit. And like I said, those are all going to cancel for whatever we're solving for. So let's go ahead and get into an example problem. Erase this really quickly. And in our example problem, we're going to be looking at methane as a replacement for gasoline. And we're going to be solving for the volume of that. So, example problem 8.9 on your textbook. Right, using the ideal gas law. So we have methane, which is CH4, is being considered for use as an alternative automotive fuel source. 1 gallon of gasoline could be replaced by 655 grams of methane. All right, so we have a mass there. Let's write that down in our givens. What is the volume of this much methane at 25 degrees Celsius and 745 torr? So right off the bat, we know we're looking for volume. We know we have a temperature of 25 degrees Celsius. And we have a pressure of 745 torr. Right. Now, right off the bat, we know we're going to be using the ideal gas law. So PV equals nRT. We have a temperature, we have a pressure, we need a volume, we have a mass, but we don't have moles, and then we have the ideal gas constant R, right? So first thing we're going to need to do is this mass in grams here is not very helpful to us. We need to convert that to moles. So the way we're going to do that is set up our mass, 655 grams, times the molar mass of methane. Now, I'm assuming you already all know how to do molar mass. You should come out to 16.04 grams. Remember, for this, just add up the molar mass from the periodic table of carbon and 4 hydrogen atoms. All that together is going to come out to 12.01 plus 4 times 1.008. So together you get 1604. All right, we're going to solve for that. And we are going to get 40.8 moles. All right, so there we have a value for N. Awesome. Next thing is 25 degrees Celsius. Now, our formula is going to require Kelvin. All right, so the way to get Kelvin is to take Celsius, add 273 to it, and for our Kelvin temperature, we get 298 degrees Kelvin. All right. Last thing we have to deal with is this torr. So for torr, we want to convert it into ATM because you'll remember for the ideal gas law, our value for R is equal to 0.08206. And then we have those funky units at the end. L ATM divided by moles times Kelvin. Since this is an ATM and we want these to cancel, we're going to have to convert torr to ATM. So let's go ahead and set that up. We have 745 torr. We put what we want at the top, ATM, and there are 760 torr in one ATM, or 1 atmosphere. Our torrs are going to cancel, and that is going to give us 0.98 atmospheres. Right? So, that's going to set us up to use our ideal gas law. Once again, we took our mass, we converted it to moles, we took our temperature in Celsius, converted it to Kelvin, and we took our pressure in torrs and converted it to ATM. Now that we have those values, let's go ahead and clear up some space and solve for our volume. All right, so once again, our value for N is 40.8 moles. Our value for temperature is 298 degrees Kelvin, and our value for pressure is 0.980 ATM. Our ideal gas law, PV equals nRT, where R is equal to 0.08206, and the units are liters times atmospheres divided by moles times Kelvin. All right, so let's go ahead and plug it in. Now to isolate for volume, we're going to want to divide over our pressure. So if we want to get volume all by itself, because we're solving for volume, we divide by P, divide by P. That's going to give us volume is equal to nRT over P. Okay, so let's go ahead and start. We have 40.8 moles with our constant, 0.08206 liters ATM. Looks like I'm going to run out of room. Divided by moles times Kelvin. And we'll stick it on this side since it's multiplication, it won't matter. 298 Kelvin. Right, and then last thing, our temperature goes underneath. Pressure. 0.980 ATM. Now our ATM is going to cancel, our moles are going to cancel, our temperature is going to cancel, and so our only answer left, or all we have left in units, is liters. All right, so liters for volume. And when you work all this out, you should get a volume of 1,020 liters. 1,020, the book writes it in scientific notation, either answer is fine, but that is how you work with the ideal gas law. A little extra conversion in there, but it's all stuff we've done before. So go ahead and get started on that homework, and let's finish 2020 strong.